We'll be live.
All right, everyone, welcome. This is the fourth lecture, and today we're going to talk about actually stochastic processes most of the time. So we'll discuss certain issues related to stochastic processes. Among them is going to be stationary. It's not going to be difficult today. Okay, we're going to see basically what this will be. First off, we're going to look at Cartesian products. This is just a technical issue where we'll look at index sets. Index sets are basically sets representing time. Okay, we will basically trying to build this up. Then we're going to distinguish between discrete time and continuous time stochastic processes, as well as discrete state and continuous state processes. You're going to see what this will be. We're going to look at filtrations, or so-called filtered processes. That's going to be important when you look at stochastic integrals. So for that, basically I would be deciding to put that in. Then we're going to look at the concept of stationarity. This is actually one of the most important issues. Stationarity means that both the mean, the variance, as well as the autocovariance of the process is going to be time independent. So we need to look at basically those things, especially autocovariances and autocorrelations in particular. And then we're going to look at some examples, easy ones. Okay, so not going to be a big deal. White noises, one of them. Martingales, I'm going to look at martingale different sequences. And then we're going to look at random walks. So I'm not going to discuss basically more specific processes like AR processes or autoregressive processes or MA processes, which denote moving average processes. That's not going to be basically a major point. We're going to discuss this when we're going to look at more, let's say, functional central limit theorems and stuff like that. So maybe I'm going to talk about those as well, but that's not going to be the major issue here. All right? Now, that's it. So that's basically pretty much it. And I'm going to start basically some technical issues. Cartesian product is going to be easy. That's not going to be relevant for the exam, by the way. This is just allowing me to actually to address stochastic processes. It's not going to be a big deal. You got two sets, let's say set A and set B, containing specific elements. Okay, those are the ones that are about. And then you will have Cartesian product of A and B first. Okay, so that's basically A by B or A times B, whatever. You can call it times, but there is actually no multiplication between sets. Okay, so you cannot multiply sets. However, you can create the so-called Cartesian product, and the Cartesian product will be simply just a correction of the pairs from those sets. So that's pretty much it. So the first pair, again, I mean, there is no specific order here, but you can basically just look into the elements. The first element is always coming from set A, and the second is going to be from set B if it's a Cartesian product of A by B, so, or A times B, let's say. Okay, that's going to be the second pair, and here you can see there is 6 of them, of course, because A has 3 elements, and B has 2 elements, and there's always going to yield 3 times 2, which means 6, okay? So keep in mind the first entries are coming from the set A, because A was named first, and the second entries will come from set B, because B was named the second. Okay, if you reverse it, so if you change it, then it's going to be a different Cartesian product. So please keep in mind that, for example, the element 3 and 1 is an element of the Cartesian product of A and B, whereas, for example, the element 1 and 3, which is not even there, is not. Okay, so that's actually, I mean, quite obvious, all right? So order matters, guys, when it comes to products like this, most of the time. Okay, let me check whether this is going to work, but it's supposed that I think it is. So, all right. Anyways, okay, let's have a look at, for example, the Cartesian product of B and A, which is different. Okay, so when you look at that, again, when you put the sets in different order, the pairs are going to be different. So the collection of pairs that you basically can generate from the two are going to be different, because the first entries now are coming from set B this time, and I'm going to start with 0 then. And the second entries are going to be coming from set A, because A was named the second. Okay, so that's the difference actually. Okay, I think this is clear now, so it's not going to be a big deal, but keep in mind this is not necessarily equal to the Cartesian product of A and B, of course. All right, so I mean, obviously. So order matters. This is not a commutative issue, as you see. So A times B is not the same as B times A in that sense. All right, again, so the first entries are coming from set B this time, and the second are coming from A. Is that clear, guys? Okay, what a Cartesian product is. Now, in this case, it's going to be different. So the element 1, 3 is an element of this Cartesian product, whereas the other is not. Okay, so that's, I think it should be clear now. So the two, actually, I'm talking about these two, are not necessarily equal. If the sets are equal, then a Cartesian product on it is going to be the same. And anyways, okay, this is a tool that I basically need to define stochastic processes because we're going to see basically a time index. I'm going to look at random variables again. You remember what random variables were? Okay, so what you need is basically actually, I mean, it was a real number depending on outcomes of a random experiment. That's the simplest definition, but it's not a complete one because in addition to this, you need to make sure that the pre-image of every Borel set is going to be measurable with respect to the sigma algebra that is containing all events of the random experiment. Okay, so those were actually the measurable sets. So again, what you do is actually, I mean, this is not wrong if you say this. You assign real numbers to elements of actually or outcomes of a random experiment. That's not wrong. Okay, so actually not at all. Okay, so you basically you have a sample space. Every random number does that. So it contains basically all outcomes of a random experiment now. And but this assignment is not just basically an arbitrary one. It has to make sure that the preimages are in the sigma algebra over omega, and that must be declared, right? So that's actually is also required. So actually usually there is a probability space which comes with it, and I'm talking about this sigma algebra here, and the preimages of the random variable or the preimage of the function capital X. The preimages of every Borel set actually must be an element of the sigma algebra. This is basically how we define it. Okay, so there is also Borel measurable space here. And if you reverse it, the preimage, again, we discussed about that, the preimage of the function of every Borel set, basically. A Borel set is actually an element of the Borel sigma algebra. And you might remember what the Borel sigma algebra was. This was from chapter 2, I think. That was actually sigma algebra generated from open intervals over the set of real numbers. Okay, so that was basically a smaller sigma algebra actually containing those open intervals. Okay, now it must be actually a measurable means that basically the preimage must be an element of that sigma algebra, right? Okay, so that is actually what the random variable was. This is a more technical definition. That's actually the easiest definition, but that is still true, however. So a real number, depending on outcomes of random variable experiment, would be actually just fine for that moment. All right? And we're going to actually extend this, so we're going to look at stochastic processes now. Of course, it has to do something with the real numbers. But in addition to it, we also have, this is true, so real number depending on outcomes of a random experiment is actually not wrong. But not just that, in addition, and you also have basically the time component with it. And that comes with the Cartesian product of omega and the corresponding index set. Okay, so capital T is going to be the so-called index set representing time, or as basically time evolves, let's say. Time is a philosophical concept, but I'm not going to discuss this here. Okay, but I think everybody should understand what this means. Okay, so now in this time we're going to assign elements of the Cartesian product of omega and the index set representing time. Okay, so that's basically the index set, how it's called. We're going to assign those pairs we're going to assign, real numbers to those pairs. And a function that does that is going to be a stochastic process now. Okay, so X is not a random variable this time. X is going to be a stochastic process now. Okay, so you have assignment, basically. All right, so the set representing time is called the index set. Okay, so that's called actually the index set, by the way. I'm going to write it down so you see what this means. Okay, it puts basically those random variables, or generates actually a sequence from those random variables where time is going to be an opponent here. And it could be, for example, looking like this. So it contains basically the elements 0, 1, 2, and so on. Okay, so for example, it could be the set of natural numbers. And now, in this case, for example, if it's a set of natural numbers, so let's say a countable set, if the set is countable, then we're going to basically refer to that as a discrete time. and the corresponding stochastic process will be a so-called discrete time process. And if it's not countable, for example, containing or consisting of an interval from the real numbers starting at point 0, for example, where it might be indicating that there is a starting value or so. It's not necessarily like that. So it could be also the set of real numbers, by the way. But the set is not countable. In this case, if it's not countable, then we call it continuous time. And the corresponding stochastic process will be a so-called continuous time stochastic process, by the way. Okay, so those are the two types now, discrete time and continuous time stochastic processes. I'm going to talk about that in a minute, but that's basically depending on the structure, basically for time. And in this case, even time is bounded from below. So in this case, it is bounded from below, okay, because it doesn't, in both cases though, okay, because it doesn't go beyond that. So this might indicate that must be a starting value of the process if it's like that. If it's not bounded from below that, you could go back infinitely far in time. All right, that would be basically just the issue with that. But this is not considered here. So it doesn't really matter whether time is bounded from below or not. But if it is, it might indicate there would be a starting value of the process. Anyways, okay, so that's basically what it was. And again, I'm going to talk about that in a minute. So when I'm trying to categorize stochastic processes, but that's basically what it does. So we have elements of a Cartesian product, and we're going to assign real numbers to those elements. And a function that does that in such a way that basically, again, if basically we're looking at the single version, if this is a random variable, okay, so when you fix basically the element of time and that this is going to degenerate to a random variable, then we're going to talk about a stochastic process. So it's not just basically a function that does that, assigning real numbers to elements of the Cartesian product, but it has to be in a specific way. And I'm going to talk about that in a minute. So this is basically what we're going to look at. So now there's different notations regarding the stochastic processes, and I'm not going to be consistent regarding those notations. Okay, so sometimes I would like to, change it depending on the purpose. Okay, so sometimes, again, this is also not consistent in the literature. So sometimes you simply just see X, okay, X denoting a stochastic process. I sometimes use that on the slides too, okay? Or you can basically, since you have an assignment here of real numbers to element of a Cartesian product, you have actually a function depending on two things. Number one, the outcomes of a random experiment, and number two, depending on time, okay? So you have a time-dependent random number, you can call it like that, all right? Or a random variable, actually. Okay, so sometimes you see that as a notation. Sometimes it's different, okay? So just xt, that's it. So you put a time index on it. Because xt is supposed to be a random variable, so x is supposed to be a random variable, and if you put it basically next to it, generated some sort of sequence maybe, that you could basically interpret that to be a stochastic process as well. Okay, or you put it basically in those brackets, and then you can simply say that there is a sequence to it. Okay, so again, the literature is not consistent regarding the notation, and neither am I. Okay, so sometimes, again, it fits different purposes. Sometimes it's basically one notation is which is practical and the other is not. So again, xt could be also a stochastic process, and then you would have just simply a collection of random variables here in this case. So that could be actually the set of random variables where you put basically an additional index here to it, and that's simply it. So again, sometimes it's written like this, sometimes it's written like this. So xt is very common. Okay, you can see that as well. Okay, so again, if, let's say, for example, time is bounded from below, and that could be more consistent with empirical applications. Again, sometimes, again, I will switch the notation. This is the notation that most common when you use continuous time stochastic processes. Well, the Wiener process would be one example, the Brownian motion. Okay, so that I see this most often, and I'm going to turn that to it. Okay, so when we look at continuous time processes, I plan to do that next week. So next week we're going to look at the Wiener process definitely, because we're going to look at limits of random walk. So I'm use that one in that case. Okay, so you see that one for continuous time processes, because again, so time index can be also different. It can be a fraction, whatever, and it's too small if you write it like this. But that is more common basically for discrete time. So that is for discrete time, very common, and that is for continuous time processes. But again, it's not a mandatory, so you can actually pick either of those. it doesn't really matter. It depends on your purpose. So simply just write x. Okay, sometimes I just simply neglect, the time index, and so on. Okay, so you see lots of different notations. I'm going to actually, you'll use those two. Okay, so those two are going to be actually used quite frequently. That one for discrete time and that one for continuous time processes. Okay, but again, I'm not consistent with that, and neither is the literature. So actually, it's both. I mean, all notations have their advantages and their disadvantages, and yeah. So, what am I supposed to do? Okay, based on that. But even that is considered or can be considered to be a stochastic process. So that's also very common, and that's also what I'm going to use. Anyway, but that statement is still true. So you assign real numbers basically to elements of a Cartesian product, but we use it basically with a specific way. So not just that. We're going to look at paths now. So paths are actually, that would be, let's say, a degenerate function. So if we fix basically the random component. So keep in mind, omega is the random component of the process. And then we basically have actually something which is time dependent. So we fix a random component, then of course you have that the stochastic process only depends on time. Okay, so that function, of course, degenerates and to a time component function. And that time component function is called the path of the process. That's actually data, so you can call it data if you like. Okay, so you can write it like this. Again, so this is not indicating a continuous time process as I mentioned before, but that's simply just illustrating that the process only depends on time if actually the random component of it is going to be fixed. So you have a function actually which assigns certain values to specific points of time, let's say, and that's called the path of the process. So if the random components is fixed, then you have basically the path. And that's it. Okay, so you can basically represent this using some graphs or whatever. I'm going to show you basically how a path would look like, but that's something you should basically keep in mind. So the random component is gone. Usually it would be here, right? That would be basically part of the Cartesian product, but that's fixed now. So since it's fixed, there is no randomness anymore. And since there is no randomness anymore, that's practically what you have, the data observations. So these are data observations, to put it in simple terms. So that's the most practical issue. Data observations depending on time. So for example, stock prices, daily stock prices, whatever, depending on basically the point of time. Okay. Now the function is not clear. So how does that depend on basically? But that's just another story. All right. So when you fix that, this is basically what you have. And then you can represent this in terms of a figure. So you put basically the time onto the time component, let's say the index set on the x-axis, and then basically the values of the process on the y-axis, and then you can get a path like this, for example. Okay, so that's typical, right, for a stochastic. It could go basically or different directions. It doesn't really matter, but this is basically data. Okay, so when you fix a random component, there is no randomness anymore. If the data is given, then data is given, point blank, period. So then you have it, and then you could do things with it, but that's not what we're going to discuss today. All right? Do you understand it, what a path is? So you take away actually the random component, and if you take away the time component, so that's the other way around, if you take away the time component by fixing it, so at a specific point of time, but not the random component, because the observation is not there yet. The random experiment has not been executed, let's say. If you fix the time component, then the function is going to degenerate to a random variable. And whether the random variable is continuous or discrete is going to decide whether you have a discrete state or a continuous state process, but that's also something which I'm going to talk about. So again, this function, depending on actually both on a random component and on a time component, if you fix a time component, it's simply just only depending on the random component. And since it only depending on a random component, then it's going to degenerate to a random variable. It must be actually a random variable if it is a stochastic, if this function, right, is a stochastic process. Okay, so that's actually the condition. So a stochastic process is not just an assignment of real numbers to elements of a Cartesian product of a sample space and the index set, okay, but in such a way that if you fix the time component, then actually the function to which it degenerates to must become a random variable. And a random variable is a measurable function, you know that, right? Basically, regarding the preimages and so forth. So that's basically what we're looking at. actually 2 or 3 weeks ago, but not going to recall it because I don't need it now. But this is a must, actually. So when you do this, it's necessary that the function becomes a random variable. If it's not, then it's not a stochastic process. But you can basically consider stochastic processes to be actually functions assigning real numbers to Cartesian products of the sample space and the index set. Okay, but that's basically to which it generates to. And you know what a random variable is. A random variable is actually a measurable function. So you know what basically you have a probability space, you have a Borel measurable space, and the preimage of every Borel set, must be actually in the sigma algebra containing all events of the random experiment. All right? So that's basically what it was. But I'm not going to discuss it today. All right? Now, again, I'm going to distinguish between two types. Okay, if you have a stochastic process, so we're not fixing time now, but let's say if we, consider time to be, or the index set to be a countable set, for example, containing the natural numbers including 0, let's say, so, but that's countable. If this is the case, then the path of the process could look like this. So when you basically look in that, there is always an interruption. So actually, this is what that would be the first observation, here will be the second, and so on. So you basically go through the observations, and that is a discrete time process, okay? Because, between, let's say, time point 3 and 4, there is no observation, right? Okay, so because there is interruption. So yeah, the set here is countable. And if the set is countable, we consider that to be a discrete time process. Typically, if you have the natural numbers around. Okay, so actually in practice, when you collect data is always countable. All right, so in practice, every kind of data or path would be actually a discrete time process. But those dots appear if they're, let's say, sufficiently close to each other, then those are to be basically connected. So when you look at, for example, continuous time processes, although it's basically simulated from discrete data, but you put them, let's say, sufficiently close to each other, they appear to be actually connected. So there's always going to be an observation at every point of time, let's say. So not just, again, from the practical perspective, it's difficult to comprehend, but for the Wiener process in particular, is going to be true. Okay, so it's not just basically observations, let's say, at point 6 and 7. There is always also observations between any arbitrary point there is. So you could specify the value of the process at any point, basically, when you look at that. And but that's more theoretical. In practice, it's not true. So no matter basically how high the frequency of your data is, right? It's always basically some at discrete points of time, right? But if they appear to be, let's say, sufficiently close to each other, then these dots appear to be connected, which, again, it is true, right? So this is typically what you can think of a continuous time process. So continuous time processes are actually more from a theoretical perspective, which interesting, right? Wiener process is one of them. But yeah, so you could have actually, and I mean, at any point of time, you could have always observations between, but not just that. So it's not a countable set. That's important. Okay, so for a continuous process, all right? The Wiener process is going to be one of them. But anyway, so you understand, I think, the distinctions between the continuous time and the discrete time process. Most of the time, we have discrete time processes. Again, so in practice, every process is discrete time. Continuous time processes are actually something for theory, okay? Because even if you increase the frequency of the data, it cannot go beyond any limits, okay? I've seen 500,000 observations per every millisecond. Okay, that's the highest frequency that I saw. That's a lot, by the way, but you cannot go beyond that, or it's hardly imaginable. Now, we're going to distinguish between continuous state and discrete state processes. So there's going to be 4 types, okay? If you fix basically the time component, so you look at the random variable to which the function is degenerating to, if you do this, then you can distinguish, actually from the practical perspective, you can distinguish between discrete and continuous random variables. We know what a continuous random variable is. A continuous random variable is actually a random variable that has an absolute continuous commutative distribution function, right? Okay, we saw that because then it has a density, by the way. So the continuity of the commutative distribution function would be not enough. However, in practice, there is just actually two types, those who have densities and those who have not. Okay, and if basically the time component is fixed, then the function is going to degenerate to a random variable. We talked about that, okay? And we have seen this before, right? So that's nothing new in that regard. Okay, so then it's going to be a random variable. However, if the random variable is discrete, then the process itself is going to be called a discrete state process, okay? And it would be discrete at all points of time. All right, so let's say, again, it could be also switching, but that's not very common in practice. So it's either discrete state or it's not. So the process is called a discrete state process if, in this case, if the random variable to which it degenerates to when you fix a point of time is a discrete one and for all points of time. I forgot to say this, but I think it should be clear now. So I'm not going to basically consider the possible case where it could change. So where, at one point of time, the random variable would be discrete and the other point of time it would be continuous. That's out of question. So it's either discrete or continuous at all points of time. I didn't put it in here into that definition, but I think it would be actually more easy to categorize this from the practical perspective, okay? And if it's a continuous one, then it's going to be a continuous state process. So if the random variable is continuous, then you have a continuous state process, right? So if the random variable is continuous, then you have a continuous state process. So those combinations, on the one hand, discrete time and continuous time processes and discrete state and continuous state processes degenerate four combinations, right? I'm going to discuss each, so you'll see basically how it would be. Okay, so first off, I'm going to consider actually discrete time, discrete state processes. Okay, so both sets are countable. Okay, the codomain of the process is countable. So for example, considering the set of natural numbers, as well as the index set. So those two are going to be countable. And if that's the case, well, again, omega does not need to be, right? But again, why would it not be? So, but that's basically what it would be. So in this case, you have a discrete time, discrete state process. And so you have observations at specific points of time, but no points of time between. It could look like this. So for example, starting here, then here, then here. So let's say the process can only take those values, right? 0, 1, 2, and so on. Okay, when you look at that, might not change even. Okay, and then it could go back. So it's not basically just, non-decreasing. It could basically go back to the bottom, right? It's not just basically, but that's how you could represent it when you look at the path of it. So that might indicate, so when you see something like this, it might indicate that the process is a discrete time, discrete state process. Number one, there is no observation between sampling points, right? So for example, between 4 and 5. And number two, there is no possibility for the process to take values between, in this case, between those two, for example. Okay, that would be a discrete time, discrete state process. But sometimes when you look at the path, it's not clear which is what. So, because if they are sufficiently close to each other, the dots appear to be connected. So, well, that's not how it would look. But anyway, so it could be the case though that it is looking like this. Now I'm going to look at another combination, discrete time, continuous state process. Okay, so then continuous state would mean that actually the random variable is continuous. So codomain is actually here, still R, and it's not countable. It could be, but in this case, if it's not, then it could look like this. Again, so this is just a representation to illustrate the second combination, discrete time and continuous state process. Okay, so the process will basically just be the same. I mean, you could make the argument that there is actually the value of the process, for example, here. Okay, but since there is no change, I will simply just affect it like that. Okay, so it could be represented like this. For example, with the step function, where actually the jumps can take arbitrary values. Okay, usually it's not going to be connected, but that's how it could evolve. Okay, so there is no change in that process. Anyway, okay, so and then you could look at the other combination. The remaining one is a continuous time discrete state process, and then you have a continuous time continuous state process. Okay, now you have a discrete random variable at every point of time in this case, and the time is not a countable set. So in this case, the index set is not going to be countable. Let's say it's going to look like this. Every real number between 0 and plus infinity. And yeah, it could be looking like that. So for example, okay, so continuous time, these dots could be, let's say, sufficiently close to each other. Actually, but they're not connected with respect to the y-axis in this case. So there is still jumps, you can see. All right, but yeah, this is just a representation, by the way. Okay, so those are the values that it can take, and z is the set of integers, so including 0, 1, -1, 2, and so on. And those are the values here of the process there is, and let's say there is no other. It needs to be just countable, okay, so then, but that's a way actually just to express it, so that could be looking like this, but continuous time. So there is, let's say, these dots appear to be actually connected. Okay, I see that the frequency was not large enough, but it doesn't really matter. This is how it is, and or how it could be. And there is also the other combination, continuous time, continuous state processes, where the random variable is continuous and time, or the index set, is not countable. And you already saw a path which would correspond to it, but this is also one of them. So it could be also looking like this, right? That's one way to look at it, basically. All right, is it clear? So are those combinations clear? Again, when you look at paths, it's not clear which is what. Okay, so sometimes I would not be able to identify myself. And keep in mind, I mean, I was faking it because those are, I mean, let's say this is a process which I simulated at, let's say, discrete or countably many points of time. Okay, so when you look at a sample like this, or the sample which is attached to that process, time is going to be countable because the number of observations is countable. Okay, but actually they appear to be, let's say, sufficiently close to each other. So again, continuous time processes are actually more or less are of a theoretical concept. In practice, actually, when you look at data, so when you look at data observations, every process could be discrete time, because no matter how many observations you have, it's always going to be finite. Not just countable, but finite. So you're not counted many, but also finite. Okay, even if you have basically a large sample. Number of observations is always going to be finite, no matter what. So yeah, this is how it will be. So I'm going to look at actually following definitions. So I'm going to look at the so-called filtrations. This is also technical. I'm going to come back to filter processes when you look at stochastic intervals. This is probably done in the following 3-4 weeks or so. Not now. But I need to start somewhere. So looking at stochastic processes, my goal is actually to define filtered processes. What we have is actually a probability space. So we have a probability space. We have a Borel measurable space. So actually you could basically generate a measurable function. And then we have an index set now this time. So index set represents time. That's always the case, right? Now, we're going to look at sigma algebras that are subsets of A. So those, not just subsets, but those are going to be sigma algebras as well. And I'm going to index them, and I'm going to collect them, and I'm going to create a family of them. So I'm going to use a family, and I'll call it the index family of those sigma algebras. So keep in mind, guys, those must be, those sets, the Fs, must be sigma algebras. You remember what a sigma algebra was? That was actually a family that was closed under complementation and closed under countable unions. which was not empty, of course. So it's a non-empty family that is closed under complementation and closed under countable unions, right? And the family is a subset of a power set. Remember that one. So, but I'm not going to discuss that here. So those have to be sigma algebras, and I'm going to collect the family of them, and basically looking like that. So that's it. Okay, so indexing it by time, and that's going to be a filtration, pulling back period. Okay, and if, but not just that, if the sigma algebras are actually non-decreasing. What does that mean? As the index t increases, you will have at least sigma algebras that are not going to be basically decreasing. So every following sigma algebra is supposed to be a superset of the former. Okay? So as if I basically increase the index, which is represented by t, k, l, whatever, okay, then the one comes next is not smaller than basically the one that was there prior. And those are sigma algebras overall. So not just that, okay, so you have basically sigma algebras that are non-decreasing. Okay, so you have a non-decreasing sigma algebras, okay, and if you collect them and put them into a family, that family is called a filtration. I'm going to give you an example which is simple. We're looking at the sigma algebras that were generated by random variables, because those are actually the ones that can be generated from them. We have seen that those exist. Okay, so again, let me just give you a little example. We have seen that those sigma algebras exist. So in this case, let's say I'm going to put or set them equal to the smallest sigma algebra that are generated from the random variable, but not just from the random variable, but from the past observations of the random variable. Okay, so the current observation as well as the past observation, depending on how far you can go back in time. So that depends on the structure. Anyway, and that represents actually the total information that is available at time point t, because this assumes that you know absolutely everything about the process until up to that point of time. Okay, so again, we have seen that this was actually existing. So, and the notation here was that. Okay, so the smallest sigma algebra that is generated from those random variables were actually up to that time point. So, and that is a filtration, by the way. Okay, because by definition, that is a sigma algebra. We know that it exists because we have even proven that. That was, I think, was the first or the second lecture, I'm not sure. So if I recall it correctly, those exist. Okay, because the intersection of countable and many sigma algebras is always going to be a sigma algebra, by the way. And that is actually the small set containing it. So there is a and this is also actually how Borel sets were defined. So Borel sets were actually sigma algebras over the set of real numbers generated from open intervals. And that includes actually the closed intervals as well, but that's something which I have shown anyway. So you can also adopt that same procedure. You have those random variables, and those random variables generate sigma algebras because those were the images, right? So, I mean, this is basically a measurable function. And since it's a measurable function, since the preimage of every single one of them is going to be an element of that actually generates a sigma algebra as well. And this is non-decreasing. And so since it's a non-decreasing collection of sigma algebras, the family containing those is considered to be a filtration, by the way. Okay, so that is one standard example that is used. It's actually called the natural filtration. So the name of that is going to be the natural filtration. Okay, so natural filtration. And an adapted process is going to be a stochastic process that is adapted to that filtration, basically, in such a way that is going to be F measurable. So at every point of time, the sigma algebra Ft, okay, or the preimage of that, is going to be actually an element of the sigma algebra. Not just A, but also Ft. And that's what an adapted process is going to be. When we discuss stochastic integrals, I'm going to recall that definition, and I will basically address that issue as well. So we're going to look at adapted processes now. A process is called adapted. Okay, so let's say you have a process, And that process is called adapted if, and that's, I mean, again, so this is what the definition is going to be. If, or to the filtration, by the way, that's actually more technical. If the corresponding random variables, so when you fix basically the time point, then the function degenerates to a random variable. We already saw that. And if that random variable is not just a random variable with respect to the sigma algebra A, which is always needs to be, right? By definition, that is always the case, because otherwise it would not be even a random variable. But it's also a sigma, basically a random variable with respect to the sigma algebra ft at every point of time, as basically the index progresses, right? And that's basically the case. So whenever basically t is fixed, the function is going to degenerate to a random variable. And if that random variable is also a random variable with respect to the sigma algebra ft contained by the filtration, then the process is adapted to that filtration. That's actually the technical explanation here. So if yt is a random variable, I mean it is always, so if you fix the time component, it's always going to be, but it's going to be measurable only actually in general case. So if it's a non-adaptive process, it's always going to be measurable with respect to the sigma algebra A, not necessarily to another sigma algebra, which is just a subset of it. But if it's also measurable with basically to, and every point of time, to, in addition, with respect to the sigma algebra ft at every point of time, which are elements of that filtration, then the process is adapted to that filtration. So it's not just measurable with respect to A, it's also measurable with respect to actually ft. Okay, so ft you can think of as a sequence. It's not necessarily a sequence because the index set is not necessarily countable, so if it's not countable, that you could not get a sequence, but let's say from the practical perspective, it's easier to imagine. If this is basically also measurable with respect to ft, not just with respect to A. So you might remember that. What does that mean? This means that the preimage of that, okay, so the preimage of that function, that's a function, right? The preimage of that, or the preimage of every Borel set of that, actually, is always going to be an element, not just of the sigma algebra A, which it needs to be as the case, because if it's not, then it's not a stochastic process, but also to the sigma algebra ft at every point of time. And that's going to actually generate the filtration. So this is actually not just A measurable, but ft measurable. A measurable means that it's the preimage is an element of the sigma algebra A, and ft measurable, not just that, but it's also an element of actually of the sigma algebra ft. Okay, so then the process is going to be adapted. Just to make clear, let's say, for example, at point 0, at the starting point. Okay, so let's use it basically an example, so to give you that one, because that might be a little bit different. At a starting point, you have the trivial sigma algebra. The trivial sigma algebra is actually the sigma algebra containing only the empty set and only the sample space. We have proven last time, or maybe 2 weeks ago, that, or maybe 3 weeks ago, if I recall it correctly, that every single algebra must contain the empty set and omega as its element, because it would not be closed under complementation, among others, right? But that's just that. Now, the only way to adapt the process to this is for the process to be a constant. That's the only way, okay? Because, again, if it's not a constant, okay, so let's say you got a process, and let's call it yt then, all right? So I'm going to use that color so you can see. Okay, so yt. And let's say time point is fixed at that time. Okay, so let's say at time point 0, by the way, at least. And it only depends on the random component, or would depend on the random component, right? But if it is a constant, I mean, the only way to adapt that process to this sigma algebra, to that one, okay, so I'm talking about f0 now, is if and only if the process is a constant. If it's not a constant, so let's call it c, and c is a real number, then you could not adapt that to the basically to to that filtration if the filtration starts at, let's say, 0.0 by the trivial sigma algebra. So this indicates that at, let's say, at the starting point, the random variable should be a constant. If it's not, then the process would not be adapted to the filtration. You understand the point? That's it. So this is actually what it would be. If it's not a constant at the starting point, the starting value, then it's not going to be adapted process, by the way. That's the example that I could make. Again, so the only way to basically to make sure that the process is adapted to the sigma algebra is to make sure that at least at that point of time the process is going to be a constant, because you could not adapt it actually otherwise to it. If it's not a constant, it would not be adapted. So that will basically give you an example for a stochastic process would not be adapted. Okay? If, let's say, and that's important, if the filtration starts here, right, like that, so at that point. You understand this now, more or less? Again, if this is basically a trivial sigma algebra, so that will be just basically addressing a constant, by the way, and that's what the adaptive process is, or would be. Anyway, okay, yeah, I'm going to come back to this issue when we look at stochastic integrals. That's going to be important. Defining specific integrals based on adapted processes. So that processes must be adapted to a filtration in general. Now, the filter probability space is just a technical issue, right? So actually what you do is you have the probability space, and if you want to call it the filter probability space, this includes a filtration to which a stochastic process is usually adapted, because otherwise, why would you actually generate the filtration if there is no stochastic process to which it's supposed to be adapted to, right? Okay, so that's the only purpose actually to create a filtration when it comes to a stochastic process, and then this would indicate that, there is papers starting with the notion that, we have a stochastic process adapted to that filtration based on the filter probability space, blah, 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 blah. So you simply just put actually a filtration to, or add a filtration to the probability space and creating a filter probability space then. Okay, so there is the notion that there is a stochastic process to which this actually is adapted to. Anyway, okay, so in this case, again, so capital F must be a filtration, otherwise it would not be filtered, so that's it. But that's just actually a technical issue, by the way. So there is, in this case, we talk about adaptive processes, by the way, so that's the main purpose. Okay, and this concept will be necessary when addressing stochastic integrals, as I mentioned before. All right. Now, next we're going to look at the autocovariance. That's an easy concept. This is actually just the covariance of the process to itself, with a different time lag. So you have two different time points. Let's say one is at time t, and the other, without loss of generality, would be at time point t plus h. And h would be the difference between the two. Okay, so there's always the difference between the two. T and t plus h can be negative. Okay, so that would mean that if t is the current point of time, then t plus h would be the past, and if h is positive, that would be some point time in the future. And the covariance between the two, if those two are random variables to which they degenerate to, if I fix a time point, then you could basically address the covariance. And you might remember the covariance, again, is, after, addressing certain properties, is the expectation of the products of the two minus the product of the expectations, or the expectations of the product of the deviation of the value of the process minus the mean. But anyway, okay, so that's simply how you would address it. So whatever that covariance would be, that is basically the autocovariance. Why auto? Because you calculate the covariance of the process to itself, only at different points of time. So that's where actually the term auto comes from. Okay, so it's self-reflecting in this case. If you calculate the covariance of a process with respect to another, then that's not auto. Okay, so that's another process. But if it's the same process, that's auto. Okay, so we call it also like that, autocovariance. And we call it basically the time difference. Okay, the difference basically between the sampling points. Let's call them sampling points, okay, because in practice you have those sampling points. We call it the time lag. So the time lag is actually the difference between the two sampling points. It can be negative, by the way. Okay? And again, how would you address it? This would be actually the expectation of the products minus the product expectation of the expectations. Okay, so the expectation of the process at time point t times the expectation of the process at time point t plus h. Or you can call it basically the expectation of the product of the deviations, right, from the current observation to its mean, as well as the other observation at time point t plus h to the mean of that. And that would be actually the expected product of the deviations. All right, but that's actually more practical when addressing basically the autocovariance of processes. And there is a notation which I use for it, sometimes gamma. Okay, so gamma refers to the autocovariance. You need to basically denote two sampling points. The one is going to be t, and the other, in this case, is t plus h. And the time lag is basically the difference between the sampling points. So t plus h minus t would be actually just h, and that's it. Okay, so that's a notation that I use. But again, sometimes, so since people are not used to it, sometimes I switch to the other as well. Okay. But in econometrics, okay, so when you do econometrics, every time you see gamma, that is mostly the autocovariance. Anyway, and there is also the autocorrelation. Okay, so you need to understand that it can depend on both basically the sampling point as well as the time lag. That is a possibility. So at different sampling point, even if the same time lag, autocovariances can change, which they usually do. Anyways, okay, so how to imagine that? Let's say here you got the sampling point, time point t, and then you got time point t plus h, and actually the autocovariance, and that's a time lag. So the difference between the two is a time lag, of course, which is h, right? So that is h, right? And I think it's going to be clear by now. Typically, if the time lag increases, the autocovariance, or at least the absolute value of the autocovariances, tend to decrease. Because actually the further you go back in time, the less past observations, or the impact of the past observations tends to be less on current observations. So for example, the stock price of tomorrow is more likely to be affected by the stock price of today than the stock price of 20 years ago for a given company, that's for sure, right? So it tends to be the case. So autocovariances tend to decrease if actually the time lag increases, but not necessarily. Okay, so it's not, but typically it tends to be the case. I mean, why would basically prices of 20 years ago would have more impact on current prices than prices of, let's say, last week or so, right? It doesn't make sense to me. But again, it just basically, so it would be possible. But that's not typically the case. And the autocorrelation is simply just the autocovariance divided by the product of the standard deviations at those specific time points. So the standard deviation at time point t versus the standard deviation at time point t plus h. Keep in mind that the square root of the variance is the standard deviation. And that can also depend on basically the time point t and basically the time lag as well. Okay, so there is basically, in general, there is dependency with respect to both. Okay, does that make sense so far? I hope it does at least, all right? So again, we're going to discuss this later on, but again, we're going to look at that one. So if basically the time point is 0, all right, or the time lag is 0, then you look at basically the autocovariance of the process at time point t versus the autocovariance at time point t, which is basically simply the variance. So then the autocovariance degenerates to the variance. You can also write it like this, so I don't mind basically you writing gamma of the process, and you simply just write t and t, right? So it's basically because h would be equal to 0 then. But that's the variance, right? Now, next, we're going to look at serial correlatedness. This is just a collection of definition. A process is called serially uncorrelated if its autocovariances are all 0. So this means that there is no linear relationship between the current observation of the process to its past or to its future observations. So the current observation does not affect future observations. and past observations were not affected by the current observation was not affected by the past observations, at least not linearly. So again, correlation only addresses linearity, okay? That's important, whereas independency is a stronger concept. But I'm going to come back to it later on. So if the autocovariances, or as well as the autocorrelations, by the way, are all zero for every time lag there is, except for the time lag zero, because if it is also zero for h being equal to zero, then of course the process would be not a random, actually a process would be a constant, by the way, okay? Because if it has no variance, then it's a constant, point blank period, right? So it has no variance, it means that the variance would be equal to zero. Anyway, but if h is not zero, so the difference between the sampling points is not zero, and the autocorrelation is zero, because the autocovariance is zero, then the process is called uncorrelated, or serially uncorrelated. You can call it serially uncorrelated. Or not autocorrelated, that's also something which I have seen. And serially correlated otherwise. So if at least there is one autocorrelation which is not zero, then it would be autocorrelated, simply. All right? So that's basically it. And keep in mind, guys, correlation only addresses relationships that are linear, not necessarily other relationships. We were discussing that already. Okay, so I just want to basically keep that in mind. In case of normal random variables, if they are uncorrelated, then they're also independent, but that's an exception. All right? Anyways, I'm going to look at stationarity. Now, stationarity is one of the most important concepts there is in time series, and we'll need to address it here also as well. Stationarity means that neither the mean nor the variance nor the autocovariance of any of the process that is supposedly be stationary is time dependent. So if there is no time dependency of those moments, I'm going to call them moments because expectation is a moment. I mean, the variance is not, but it has to do with the second moment, so basically you can address it like that. So neither the expectation nor the variance nor the autocovariance of the process will be time dependent. Then the process is called stable sometimes. And in the weak sense, because strong sense stationarity addresses cumulative distribution functions, which I don't want to include in here. That's not a practical concept, so CDFs are not practical in this case, right? Because usually when you look at or observe data, you don't know the distribution from which it's coming from. But you could estimate the mean and the variance at least, right? So that would be actually still possible. Anyway, so a process called stationary if, and that's going to be the issue, the following conditions jointly hold. It needs to be addressed. It must be true for every single there is. The mean of the process, so starting with number one, the expectation or the mean, you can call it, must be finite, and it must be time independent. So it doesn't depend on time. Whatever it is, it's not supposed to depend on t. Okay? Then the mean would be a constant, by the way. So for example, there is no linear trend in the data. If the expectation would be depending on time, for example, let's make an example here. So for example, it could be like that there is a trend in the data. So that would be a linear trend, okay? Then the process would not be stationary. So for example, when it's looking like this, so a plus b times t, that would be the expectation, which would indicate that there is a linear trend in the data, right? That's not a stationary process anymore, point blank period, because it's not supposed to depend on it. It must be a constant. If it's a constant, then it's going to be, I mean, it's a finite, right? It must be finite, right? That's also true, but let's assume that it is. Okay, no matter how large it is, it would be finite. If it's finite and time independent, so there is no t in here, then at least it satisfies this condition, and if it satisfies in addition all 2, which comes next, then it would be also stationary. And that must be true for the variance as well. So the variance is also stable. You can call it stable if you like. It doesn't change by time. So the expectation doesn't change by time. If it has a linear trend in the data, then it does. Or seasonal data, it does. But if it does not, then actually it would be necessary for stationarity. Not sufficient, but necessary. All right. Number 2, the variance, the same. The variance is not supposed to be time dependent. If it is, then the process cannot be stationary. Right. So when you have, for example, a volatility that is stochastic volatility, right? Unconditionally stochastic, then there is no way basically for actually avoiding or ensuring stationarity, by the way. It can be conditionally stochastic, that's a different thing, but it must be actually unconditionally, right? So it must be a constant, by the way. Whatever that is, it must be a constant. If it's not a constant, depending on time, then it cannot be stationary. And the third component is that the autocovariances must be time independent as well. However, they can depend also, here you see it again, okay, so since you might not be used to that notation, it's not supposed to be time dependent, okay? So it's basically, it does not depend on time, and it is finite too, all right? So, I mean, if it's uncorrelated, that would be automatically fulfilling it, because if it's uncorrelated, then the autocovariances are 0, and if the autocovariances are 0, at least this condition would be actually fine. Okay? But let's say basically the other two must be also true as well. However, and that's something which needs to be stressed here, for stationarity, you can have basically dependency with respect to the time lag. So it can depend on a time lag. There is a possibility for that. But it cannot depend on the sampling point. Okay? So, I mean, typically, even for stationary processes that are autocorrelated, observations that are close to each other tend to have basically more higher degree of dependency than observations that are further away from each other, right? Which intuitively clear. However, this is not actually a necessary issue, but that's basically what at least would be consistent with reality then, okay? So keep in mind, guys, the autocovariance as well as the autocorrelation can depend on the time lag. So the distance between the sampling points. But it cannot depend on a sampling point itself. Okay, so only the distance is what matters between the sampling points, but not basically the points of time at which you're looking at it, at least for a stationary process. I'm not sure if you understand that. Anyway, if a process satisfies all three conditions, then it's going to be a stationary process by definition. And if it's not, then it's not, point blank. So if at least one condition is violated, then actually the process would no longer be stationary. So every condition must be honored in this case. You understand the point? Okay? Now if you're not sure what this means, I'm going to give you some examples, or let's say look at paths of data that appear to be actually non-stationary first. Okay? So, for example, this process, okay, what you're about to see is going to be mean stationary, at least. So the mean is going to be time independent, and at least appears to be. Again, nobody knows what nobody knows, so maybe in a future point it could change. That is also possible. But if you look at the path of this process here, at least the mean of the process, which could be, let's say, represented by this line. I'm not sure, but it could be an estimate for it. The process evolves around that, and that is not depending on t, right? So that function does not depend on t, which indicates that the process would be at least mean stationary, which means that the mean is not depending on time. You understand the point? Okay, so this is a constant function, and if it is the mean, again, nobody knows if it's true or false, and nobody knows how the future observations of the process might evolve. So it could be that after that there is a structural break in the data, but again, nobody knows what nobody knows, you see. So that's why I was writing it here. It appears to be time independent, but it doesn't necessarily mean that it is, because we don't know it actually from data. You understand what I'm saying? So in practice, we don't know what the expectation is. We only know what the arithmetic mean is, but we don't know what the expectation of the process would be. I mean, nobody's going to give you some density, right? You understand the point? So when you have data, you have data. You don't have the density, right? Or do you don't have the distribution? Maybe it's not continuous, but again, you understand the point. So nobody's going to attach the density to it, right? So that's why I'm saying it appears to be time independent at least. But the process is not stationary. Why? Because the variance does not. Okay, so again, there is basically, you can call it volatility clustering, where you have basically time frames where with lower and with higher volatilities, right? So the variance does not seem to be time independent. There is a way to test this. We're going to talk about that as well. So how to test stationarity, because it could be just, maybe some small fraction of that. But there is a way to test this. But again, the variance does not seem to be time independent. It appears to be time dependent here in this case because, again, it might change. This is not the variance, by the way. This is just, illustrating the variance. So variance is illustrating basically the expected square deviation from the mean. You understand the point? This is not it, but it kind of symbolizes that. The mean is the mean, right? But the variance is addressing the deviations from it. And it depends, right? So it's changing, or it could be changing, you see? Anyways, yeah, that's not basically what that would be. Now, regarding variance stationarity, in contrast, the process is not going to be stationary because the mean will appear to be time dependent this time, but the variance is not. Okay, so when you have a trend in the data, it could look like this. It's not necessarily a linear trend, by the way. Maybe it's a linear trend, but maybe it's not. So when you basically estimate the trend here, representing it, okay, maybe a parabola or something, again, depends. It's clearly time dependent. So it basically appears to be time dependent at least, right? Okay, it's basically for when time increases, the expectation tend to decrease. All right, that's basically what this appears to be the case. So it cannot be stationary anymore. There is a trend in the data. It's not necessarily a linear trend, but there is a trend of any some sort. Okay, but the variance seems to be stable over time. So the variance is time independent. Now, a process like this could be called variance stationary. You understand? So actually, deviations from the trend appear to be stable, right? Again, at least. Again, nobody knows what nobody knows, as mentioned before, so nobody knows what will happen after that. But until, let's say, up to this point, you could make the assumption that the variance is stable when you look at the path of the process. All right? You understand it? So the mean is going to be actually time dependent. Now, there is no way to address autocorrelation directly from the path. Okay, so I try to basically incorporate it. It's just you use, in practice, you use correlograms to address that issue, but I cannot do it here. So that's something which you cannot see directly from the path of the process, whether there is some basically time dependency or not. Anyways, not directly in every case, by the way. Now, I'm going to look at basically different notations as well, because if the process is stationary, then those moments will not depend on time, and the autocovariance, neither the autocovariance nor the autocorrelation will depend on time. So in this case, you can take it out from the notation, and that's basically what I would do. So in this case, again, those can depend on the time lag, however, they don't depend on the sampling point. And so this means, again, so I want to basically stress this because you might not understand this. If the time lag between T1 and, okay, so there you have these sampling points. There is T1, there is T2, there is T1 plus age, and there is T2 plus age as well. So the time lag is the same between those sampling points. I'm talking about those two. Okay, so those two and, of course, those two. The time lag is the same, right? And if the process is stationary, the autocovariances must be the same between those sampling points. So the autocovariance, and that's basically what I want to stress here, okay, of the process, between those two sampling points, so T1 on the one hand and T1 plus H on the other, must be equal to the autocovariance of the other, basically between the other two. And that will be T2 here and T2 plus H on this side, you see? That must be the case if the process is stationary. Otherwise, it would not be stationary. All right? So the dependency between those two must be the same as between those two. Right? This means that, you don't have actual dependency out of the sampling point. This is actually what I've written down here, if the process is stationary. So in case of stationarity, that must be true, right? So again, this must be the case, right? So it doesn't depend on actually the sampling point. It only depends on the time lag between the sampling points. But the autocovariance does not depend on at which point of time you're looking at it. Basically, it only depends on the distance between the sampling points, right? And hence, I will basically write it like this. So simply just basically addressing the time lag. No more basically the sampling points, only the time lag. So whenever you see this notation might indicate that there is a stationary process around. Okay, because its autocovariance does not depend on time. It can depend on the time lag, by the way. So there is a function depending on the time lag, which usually it is. But if the process is stationary, it does not depend at least on the sampling point. It only depends on the time lag between the sampling points, but not on the sampling point itself. Do you understand that? Okay, so then I will change the notation for both, for the autocovariance as well as the autocorrelation as well, in this case. So I will basically drop T in that case if it's stationary. Why would I use it if it doesn't depend on it either? Okay. Now we're going to look at actually the so-called invariance of the time shift for the time lag. What does that mean? It means that whenever there is a stationary process, it doesn't matter whether you'll consider basically future autocovariances or autocovariances in the past. So in particular, I want to basically be very specific here. The autocovariance with respect to the time lag h is going to be the autocovariance with respect to the time lag negative h. And the autocorrelation with respect to the time lag h is also going to be, accordingly, the autocorrelation with respect to the time lag negative h. So that's a statement that I'm trying to make here. So when I basically go backwards, those two are going to be the same because the distance between those two and those two are the same. And that's the point. So the autocovariance with respect to the time lag plus h is going to be the same as the autocovariance with respect to the time lag minus h, even if basically t is the reference point of time. So it's only the time lag that is different in this case, but only, and keep in mind, only if the process is stationary. Because if it's not, then it can depend on the sampling point, right? But if it's stationary, then it doesn't. So it only depends on the difference between the sampling points, which is both h, whenever you basically calculate the difference between the two. Okay, so here it is h and here as well. That's a distance between the sampling points. In both cases, the distances are equal. Okay, I mean, you know what the distance function is, right? So, I mean, we talked about that as well. So the distance between two is the distance between those two, right? But again, all right, so these equalities actually are not necessarily true for non-stationary processes, by the way. Again, I must stress this in general, but it can. So it can be even true, but not necessarily true. But for stationary processes, it is true. Now, that's called invariance of the time shift. Okay, so those equalities here. This is how it's called, right? And I want to prove them. So I want to look at basically the autocorrelation first. Okay, because again, it's also implied by the autocovariance, but again, I'm going to look at the autocorrelation with respect to the time lag minus h. The sampling points were actually, the sampling point is t and t minus h. Those are the two. Okay, so you will need to calculate the standard deviation at point t and the standard deviation at point t minus h. Now, if the process is stationary, and that's something which I need to stress here, those two are going to be equal because the variance does not depend on time, right? And it's neither the standard deviation. But I will ignore that because, again, why? Okay, so I will basically just change it. Actually, though, the covariance is a symmetric function. So the covariance of A and B is the covariance of B and A, by the way. And so I could simply just change the indices, which I do basically for practical reasons. I'm going to do that for the standard deviations as well. So then comes the standard deviation first of t minus h, and then comes the standard deviation at time point t. Those will be equal, but that's just a different story. And then I'm going to substitute t by t plus h. Why? Because it doesn't depend on time. It is stationary. So since it doesn't depend on time, I can basically consider any point of time that I want to. And I could change it, right? And that's what I'm doing. So I will basically substitute t for t plus h, which means that t minus h becomes t plus h minus h, which is t. Okay, so that's what you will see. Okay, I mean t plus h minus h will be t after all. And t becomes t plus h, right? So that's basically, it says literally, right? That's it. It's not a surprise. And so t minus h becomes t plus h minus h, and t becomes t plus h after all, right? So that's how you would substitute. You can, because the process is stationary, so those moments, let's call them moments, don't depend on time. And yeah, so you can calculate it. Now, t plus h minus h is t, of course. And yeah, and that is also true for that. And this expression, however, is the autocorrelation with respect to time lag h, by the way. Okay, so those two must be equal. So that's basically the invariance of the time shift. You understand that now? Okay, so in the general case, it could have been done easier because I realized, okay, I was overcomplicating it. But the fact that basically I did is basically for stationary processes, the autocorrelation simplifies because the covariance, again, is here. That's the autocorrelation, covariance. And it is going to be simply just divided by the variance because the standard deviations are equal. You understand the point? So since the standard deviation, okay, or the variances are also equal, so the variance at time point t is equal to the variance of the process at time point t plus h. The variance does not depend on time. Okay? Right? You understand? So it doesn't depend on a sampling point. And the standard deviation at time point t times the standard deviation at time point t plus h is going to be the variance, right, of the process. So you can simply just basically simplify it. And yeah, you can also write it like this. The variance is actually the autocorrelation with respect to time lag 0, if the process is stationary, of course, right? So that's the notation that I drop here. And that's also the reason why it doesn't change. Again, because the autocovariance doesn't depend on time either. So it could have been also easier. I was overcomplicating it, but again, it doesn't really matter. And yeah, that's basically what it would be. Okay, now, before we take a break, I want to address the so-called asymptotic version of stationarity. The weak sense stationarity was as follows. So a process is called, again, that was already done. So a process is called stationary if the following conditions jointly hold. The expectation is finite and doesn't depend on time. The variance is finite and doesn't depend on time. And the autocovariance is finite and doesn't depend on time. However, it can depend on the time lag. That's what we saw. Okay, so let's recall that. And I'm going to start from here because this is something which you've already seen. And I'm going to basically call out the asymptotic version. That's a weaker concept. The asymptotic stationarity simply just argues that a process is called asymptotically stationary, at least, if the limit of the expectation is finite and time dependent. Okay, as basically time increases. So as time increases, at least the expectation, a limit of the expectation is going to be time dependent. This can be addressed to be some sort of stationarity in the long run. So maybe it's not at the beginning, but as time progresses, you know, the mean is going to be stable, more or less. You understand the point? That's basically the asymptotic version. That's a weaker concept, by the way. But mostly it's fine. Okay, so, and it's finite and it doesn't depend on time, of course. So it cannot be that the limit is going to be infinite. That's not going to be happening, because if the limit is is infinite, then it's not a limit. That's a contradiction in itself. But anyway, the variance, or the limit of the variance as time increases, must be at least finite and time independent. And same is for the autocovariance. There are processes which are asymptotically stationary, but not stationary, right? Because you have a time component, for example, inside the mean, but that's going to disappear. Now, when you have a linear trend in the data, it doesn't disappear. So the trend will not disappear in the long run, right? You have maybe something like, I don't know, maybe, I mean, that could be the case where you would have something like this, just to give you that idea. So for example, when you have convergence to zero, the expectation of the process could be, I don't know, 1 minus, let's say, a certain parameter, which I call a to the power of t divided by 1 minus a or so. That's not a stationary process because you have a time dependency, but if the absolute value of a is less than 1, then this expression will converge to 0. So then it's going to disappear. And if it disappears, then the mean will be finite. Okay, so if a is finite, then it's also going to be true. But if the absolute value of that is less than 1, then it is true, definitely. And it's going to disappear in time. So the mean is going to be stable in the long run, at least. And same can be also constructed for variances as well. Okay, so sometimes you have things like this, which is actually a weaker concept, and it happens more often than you think. Okay, now let me basically just summarize this thing. If it's stationary, then it's going to be also stationary asymptotically. That's not avoidable, right? And asymptotic stationarity can be actually regarded as stationarity in the long run. So maybe not basically in short term, but in a long run, it would be actually stationary. So then you could basically ignore that issue with the time dependency of the mean. So most concepts that are actually true for stationary processes, such as, regressions and all that stuff, are going to be also true for asymptotically stationary processes. So that's a weaker concept, but still actually sufficient in most cases. All right, let's see. Okay, now I'm going to look at white noises after the break. So let's take a break now, and we're gonna basically continue after that. So, well, let's have a break of 15 to 20 minutes, if you like, and then we're gonna continue, okay? All right. Okay, so we are gonna continue with the white noises, right? That was the white noise process, which I think, sorry for this, I was a little bit too optimistic here. White noise process was maybe here, not sure. There it is. Okay, good. Now, all right, so let's continue with that. What is a white noise? A white noise is basically a stationary process with a zero mean that is not autocorrelated, and that is actually having a constant variance. So the expectation of it is 0. Its variance is a constant. Okay, it's not necessarily associated with a normal distribution. So just because it's C sigma squared, it's not necessarily based on normal distribution. However, it could be. And again, so this is just a parameter, and of course it is not autocorrelated. So for every actually oral time lag, it is going to have 0 autocorrelation, which would be the case. Okay, this is typically used to model some errors. We're going to use this also when developing random walks, and especially the Wiener process from it. But that's just basically what it would be. Okay, so we call it the white noise. It is actually a stationary process because, as you see, none of these depend on time. So neither the expectation nor the variance, nor the autocovariance of the process does depend on time. Now, since basically, so that's basically, I'll just try to summarize that. So those things are finite and not time dependent. The noise is stationary, obviously. So that is one example. for a stationary process. If you want to look at its path, okay, so that's typical. I mean, I was looking at basically noise that has zero mean and the variance would be equal to 1. This is how it actually would, I mean, that was the path that I was generating. Okay, so here is the mean, which would be actually 0, or was 0 when I was simulating it. And the variance was equal to 1 in this case. Okay, so again, of course, you can see that this is going to exceed. Again, the variance is the mean of the square distances of the process to the mean. Okay, so here in this case, it would be estimated by the mean of the squares, typically. All right, now, okay, in this case, this is what it was, and we're going to discuss it. Now, of course, it is stationary. We saw that. And also asymptotically, of course, because anything that is stationary is also going to be stationary in the long run. It's not a surprise. Okay, well, basically we'll see this. It's not true the other way around typically, but in this case, it is going to be asymptotically. Now it's going to be uncorrelated by definition, but not necessarily independent. So I want to basically stress this because uncorrelatedness does not imply independency. Independency implies uncorrelatedness. Independency was, and maybe you remember that the joint cumulative distribution function, two random variables are called independent if their joint cumulative distribution function is equal to the product of their marginal distribution functions. But that's not a straightforward or practical concept. So, but again, this must be stressed here. So not necessarily independent. Uncorrelated, this means that there is no linear relationship between the observations of the sampling points, but just because there is no linear relationship between them, it doesn't necessarily mean that there is no relationship between them at all. So uncorrelatedness does not imply independency. However, if they are independent, they are also uncorrelated. And independence is a stronger concept, but you can use this in this case. So if they are independent, then we also write their IID. So independent and identically distributed, by the way, that is also true, but it's actually enough if they have the same moments most of the time, right? So it might changing the distribution, however, but not changing those parameters. So actually it's not very correct because IID means independent and identically distributed. Identical distribution is not necessarily the case though, but in practical considerations, it doesn't really matter which distributions the noises do follow as long as they're independent, by the way. Okay, now we're going to look at martingales. Martingales are processes where the best predictor for future observations would be the current observation. That's the most easiest way to define them. Okay, so if you want to basically forecast the future observation, the best predictor for it would be the current observation. So I'm going to look at actually stochastic processes that are called martingales, but there must be also actually another condition which is to be satisfied. Number one, the expectation of the absolute value must be finite. This ensures also the finiteness of the variance. So if this is true, then basically you could also show that the expectation, both the expectation as well as the variance, is also going to be finite as well. That is also referred to be as absolute summable. So the process would be absolute summable, by the way, but the expectation of that basically variation would be finite. That's number one, but that's more or less a technical issue. And number two, the conditional expectation of some future observation. So let's say t is the current at the current point of time, and t plus s is some future point of time as long as s is greater than 0. Okay, so that's going to come, you're going to see it, but that's basically the way to express it. Now, the expectation of some future observation, given the current observation, but not just the current observation, you might remember. So you can condition that to the sigma algebra ft. That is actually a filter process here, by the way. So given the information that is available at time point t about the process, this is basically what it means, including the current observation of the process, but not just the current observation of the process, the total past. Okay, this is basically represented by it. That's going to be actually a random variable, by the way. And this conditional expectation, given basically the past, so this is just a representation, would be equal to the current observation of the process. This is not specific, so it's not even there yet. But if that is true, actually for every point there is, then the process is called the Martingale. So this means that basically the interpretation of that is as follows. The best predictor for future observations would be its current observation, by the way. Okay, so the current observation would be the best predictor for the future observation. That doesn't necessarily mean that future observations are going to be equal to that current observation. But regarding their conditional expectation, this is basically what it is. A conditional expectation is some prediction of future observations, given basically the current observation as well as the past. Okay? Now, I'm not going to define basically conditional expectations conditioned on sigma algebras. This is a very, very theoretical and very abstract concept. But I want to stress it because you need to have some Lebesgue integrals that are involved, which I don't want to discuss here in this point. But you should basically associate it. So I want to focus on applications rather. You should basically associate it with the expectation of the future observation given its past at time point t, including the observation at time point t as well. Okay, but in case that there is a possibility for that to be still random. So it's basically would be the case that, hypothetically speaking, that the current observation is not there yet. So that could be also included. So the conditional expectation is a random variable. It can be a random variable as long as basically those conditions are not specific. Whereas the unconditional expectation, it never is random. So that's never going to be a random variable, whatever that is. The unconditional expectation is never random, but the conditional expectation can be. And that's basically the point that I want to stress here. Okay, you should not bother basically with the condition regarding the sigma algebra, which I talked about. In this case, we're going to set this to be equal to the smallest sigma algebra generated by the past of the process. So every observation from the past would be actually play a role to generate that sigma algebra, but not just that, but also the current observation. So this is typically represented, or basically expresses just the total information about the process or up the behavior of the process up to time point t until then. Okay, and assume that this is known, so you know basically what it would be. The future observation would be equal to actually, if it's basically conditioned on the current point of time, let's say, that would be basically just simply the current observation at time point t then. Okay, so time point t is basically the current point of time, and if s is greater than 0, that will be some future observation. That's it. Okay, so that is basically what it would be. And if a process satisfies those two conditions, then it would be a martingale. The first one is more a technical one. So that is actually addressing the issue that, among others, the variance and both the mean and the variance of the process would be finite, the unconditional ones, by the way. But that is more just a technical value. So in this case, today's value, okay, so the observation, the current point of time, is the best predictor for some future values. Not just basically the observation tomorrow, but every observation actually up to that point. If this is the case, then the process could be considered to be a martingale. And if it's not, then it's not, obviously. All right, now I'm going to also look into martingale different sequences. That's going to be the next one. And martingale different sequence is actually the increments of a martingale. That would be it. So if you look at basically the martingale, its increments are going to be those different sequences, where actually the increments will have, conditionally speaking, 0 mean. I'm going to call it basically a martingale difference sequence if the expectation of its absolute value is finite. That's number one, ensuring basically the finiteness of the mean and the variance. So that's among others, which is a technical issue. And not just that, but basically the expectation of the future observation would be basically predicted would be 0. And that's it. Okay, so if that is true, basically you would assume that the process actually would not change, maybe, right? If that's the case, right? So in this case, that would be also true for the martingale, but not just that. That would be actually equal to 0. Because there is a relationship between that. So if x is a martingale, then the increments of the martingale would be actually martingale difference sequence. I'm going to basically address this issue. So that is actually referred to the difference operator. Okay, so the expected value, the conditional expectation of some future observation would be actually equal to 0 then. Now, it doesn't necessarily mean that the process is stationary. So I want to stress this because I forgot to mention this before, but the martingale is not necessary. Neither a martingale nor the martingale difference sequence is a stationary process. Why? Because the variance can be time dependent. It is it can be. So that's a weaker concept, by the way. All right? So just because the expectations, let's say in both cases, would remain the same, conditional expectation doesn't necessarily mean that the process would be actually a stationary one, because the variance can be time dependent, very much so. All right? Now, again, but it's not necessarily the case though, right? Now, I'm going to look at the difference operator. You might not be familiar with that. So I'm going to look at two different processes, and one would be the increment of the other. If x is a martingale, then there is a possibility to show that the increment is going to be a martingale difference sequence. What is the increment, by the way? So I'm going to look at basically process y. The increment is actually the current observation minus some past observation at point t minus 1. So at time point t minus basically at time point t minus 1. So if these are daily observations, the difference between the observation of today and the observation of yesterday would be the increment of the process. And in this case, if x is a martingale, and you would look at the increment of the process actually reflected by the difference operator, which is denoted by delta. So delta xt is actually the day increment. So this represents the increments of the process. Then it can be shown that basically the process y, which constitutes the increments of x, okay, we're looking at the difference operator, is going to be a martingale difference sequence. I'm not sure if you understand the term with the difference operator, but let's say, again, I'm going to take an example so you might be basically understand this better. So let's say you have these time points, and then you have the observation at time point 1, at time point 2, at time point 3, and so on, okay? And the observations of a process, it's not necessarily martingale, by the way, but not sure if you understand that. The observation at time point t were, maybe documented or so, there were, let's say at time point 1 it would be 10, at time point 2 would be 30, at time point 3 it would be 20, and at time point 4 it would be 50. All right? Now, if you look at the increments by now, so you look at basically the increments of the process, right? At time point 1 there is none. And at time point 2 there is just 20. And there is this minus 10, negative 10, right? That would be the increment here. And then it would be 30, because that is, again, so if you're not sure, this is 30 comes from 50 minus 20. That's the increment, basically. So how the process actually changes. And that is reflected by or can be addressed by the difference operator, by the way. You understand the point? So this is actually calling differentiation of the process. So you differentiate the process, meaning that you look at the increments. How actually the increments of the process did evolve by time. Okay? If the original series consists of 4 observations, then there is 3 changes. So there is 3 increments of the process. You understand the term now? Okay, so that's basically what it would be. The current observation minus the previous observation would be the increment of the process at the current observation. Okay, so if let's say stock price was $10 and today it would be, yesterday, today $30, and it changed by 20. You understand the point? So that's basically what the increment of the process is. Now, if x is a martingale, then its increment is an MDS, martingale difference sequence. Okay? That's basically the issue. And that is also true the other way around. Okay, then you would go basically integrating the process. So when you calculate the increments of the process, you're differentiating it. Okay, so this is differentiation. And when you go from the increments to the process itself, that's called integration. All right? Anyways, all right, so that's basically what, just a little side note here so you might understand this better. And yeah, so if X is a martingale, then its increments are going to be MDSs, okay? Martingale difference sequences, and vice versa. That is also true. Okay, now there is another issue with basically MDSs, but I'm going to look at martingale difference sequences now. Okay, so if, let's say, a stochastic process is a MDS process, or martingale difference sequence, then what? Number one, its expectation is going to be 0. And the unconditional one, not just the conditional one, but the unconditional one. And the autocorrelation is going to be, you can see this also 0 as well. So it's not going to be autocorrelated. All right? It could be basically tempting to assume that it is stationary, but it's not necessarily stationary because the variance can be time dependent. Okay? At least, but it's going to be uncorrelated. And this is a very weak assumption, by the way. Okay? So to assume that to be basically to have an MDS process, weak in the sense that it doesn't require much. Okay? So if you assume that a process, or let's say noise, is an MDS, which not a white noise. White noise is a much stronger concept, right? Then, if you just want to have basically 0 mean and uncorrelatedness, you can basically assume that you would have an MDS process instead. Okay, which could be, again, so you're not supposed to put too many restrictions on the model. And sometimes noises, if they're assumed to be MDSs, should be fine. Okay, also. Okay. However, MDSs are not necessarily stationary. I wanted to stress this before. And variance can be time dependent, which can be the case for so-called arch processes. All right. Whereas actually for arch stands for autoregressive conditional heteroscedasticity. So in this case, conditional heteroscedasticity means that the conditional variance is time dependent. Autoregressive means it depends linearly on its past. And conditional heteroscedasticity means it's conditional variance. So the variance of basically of some future values given in the past. Conditional variance can depend on time, for example. Heteroscedasticity means that it changes by time, mostly. So if this is addressing a time series. I'm not saying it is, but again, it's not necessarily stationary. That must be stressed here. So the variance can be time dependent. Which is, again, so if you assume a process to be an MDS, this is a very weak assumption, by the way, so you can just simply actually get that in this way. All right, now next I'm going to look at another property which is basically showing that. So I want to look at basically, since this is actually a more straightforward case, right? So given the current observation given its past, and of course this expectation is 0, right? This includes actually the sigma algebra. However, this is a very specific one, but it basically illustrates one thing. You can take those out, so any past observation can be taken out from the expectation operator, assumed to be as or treated as to be a constant, by the way. And if you want to calculate the unconditional mean of a random variable from its conditional mean, you can do it by using the so-called law of iterated expectations. I'm not going to use it quite frequently, so I wasn't sure basically to incorporate this or not, but maybe I can do it. It's called LI. It's called law of iterated expectations, and it says the following: the unconditional expectation of some random variable, here in this case, I'm calling it y. I mean, again, stochastic process can be treated as a random variable at a specific point of time, is going to be equal to the expectation of its conditional expectation. So the expectation of the conditional expectation of a random variable, conditioning on another, it's equal to its unconditional expectation. This is basically shown or actually applied by the law of iterated expectations. And I'm going to apply this here to calculate the unconditional expectation of basically of the process, which is supposedly be 0, by the way. So that was it. Okay, but I'm going to basically address that. And yeah, so I'm going to look at the law of iterated expectations, called or used by the acronym LI. Okay, so law of iterated expectations, you can clearly recognize why, is stating exactly that. The unconditional expectation of a random variable in general, but also of the process at time point t, is equal to its expectation of its conditional expectation. So you put basically the conditional expectation here. And since the conditional expectation was 0, because that was basically the property of an MDS, okay, so an MDS process has a conditional expectation 0, it's going to be, the unconditional expectation is also going to be 0. That's it. Now, so that's basically number 1. Number 2, what about the autocovariance? I'm going to show that it's going to be uncorrelated. The autocovariance at time point t versus at time point t plus h, again, is going to be the expectation of the products then. Why? Because, I mean, the product of the expectations, they are going to be 0. Okay, so that is 0 and that is 0. Both are 0. Why? Because, again, the unconditional expectation is 0. That was shown. So you need to basically take care of the expectation of the product. Now, usually I would use the joint distribution, for which I don't need, because I'm going to apply the law of iterated expectation again. Whenever an unconditional expectation comes up, okay, you can apply the law of iterated expectation, because it says that the unconditional expectation, again, let me repeat that, the unconditional expectation of a random variable, let's say, is equal to its, actually to its expectation of its conditional expectation. That's it. Okay, so that's basically the law of iterated expectation. Writing it down again. So I'm going to apply this for, actually for the product of those two. That's still be possible. Okay, and that's basically what is going to happen here. So I'm going to apply the law of iterated expectation again, using basically on this expression for the conditional expectation. Okay, but let me stress this. Okay, I was not doing that here. I was taking care of the unconditional expectations first. The product of the expectations is not equal to the expectation of the products, by the way. So I'm going to basically take care of that by using the law of iterated expectations again. This basically clearly states that the unconditional expectation of something is equal to the expectation of its conditional expectation. That's it. So you have that basically inside, conditioning on basically the current observation now with its past. Okay, so I'm going to basically take care of that in this case. Now, all right, so then after all, if you incorporate the current observation also, which is here, then you can take that out from the conditional expectation. Why? Because it's assumed to be known then. Okay, so if it's known, basically generated by it, then you can take it out or you can treat it as a constant. And because since this applies to the expectation of a linear transformation, this is going to be the linear transformation of the expectation. So here you have the condition. Here, since it is basically part of the condition, you can take it out from the expectation operator. And then you're left with the conditional expectation of the process at time point t plus h, but that's 0. As we have shown here, that is also true if the time point is t plus h. It's not going to be something else. So then you'll have basically the expectation of the process at time point t times 0, which is actually 0 after all. Okay, expectation of 0 is going to be 0. All right, so this means that the process MDS, all right, MDS is uncorrelated, you see, but not serially independent, by the way. That's also basically the issue, all right? I was applying the law of iterated expectations to get those unconditional expectations, by the way. And that's a tool that sometimes I use to address it, but basically you will not need this very often, okay? So you will not basically, whenever basically this comes up, I'm going to stress it, but that's not an econometrics class, so since it's not econometrics here, I'm going to just basically use it here and there, but not all the time. Now, I'm going to look at random walk process right now. Okay, maybe I have a half an hour for that. Will basically be fine. A random walk is simply a stochastic process that can be expressed as follows. There's multiple ways to represent it. So at time point t is going to be equal to its previous observation at time point t minus 1 plus a noise. And that noise is at least, again, a white noise. Now, it's, if you look at the shortest version, it's IID. Okay, so we can basically make that assumption that it's IID. Usually would not be necessary for independency because, again, it's a very strong assumption, by the way. Uncorrelatedness would be fine, but we're going to make the assumption that the noise is IID this time. Okay, again, for a random walk, it doesn't need to be. Okay, so that is a specific random walk with IID noises. That's how you would refer to it. But noises, it needs to be actually at least uncorrelated in this case. And this is basically what the random walk would be, simple as. Okay, so you have basically the past observation plus some noise. And that generates a random walk. I'm going to show you later on that the process is not going to be stationary, by the way. So that is basically another process which is not going to be. So that's basically definition number one. And number two, okay, we're going to look at the random walk with basically where you would have to have with a drift parameter. And that incorporates a constant. So not just basically the previous observation plus a noise, but then with a constant too. Okay, so that's a random walk with drift, and then, of course, the previous one without a drift. If I say random walk, I mean that is also associated with random walk with a drift. It's not necessarily clear whether it has a drift parameter or not, but in general it has. And that's basically what I'm going to look at. And yeah, so that's pretty much it for basically for now. And I'm going to basically assume that this is going to be a constant. Now, of course, if this parameter delta is 0, then you're going to basically just degenerate into a regular random walk without a drift, of course, right? Now, I'm going to look at some paths or representations first, okay? Because before I address stationarity, I would not need to have a representation that is recursive. That's the recursive one. So it has basically some past observation of the process in it. Recursive, right? So how would you basically look at it? Now, it is clear that basically regarding the representation of the random walk, however, and that's something we're going to look at, let's say that the observation at time point t minus 1 can be expressed accordingly. So I'm going to look at basically the case where there is no drift first. That's easy to deal with. This is actually let's say, the observation at time point t minus 2 plus the noise at time point t minus 1. Again, so if you substitute t by t minus 1, then you will have t minus 1 will be t minus 2 then. And then you'll have t basically becoming t minus 1. And what I'm going to do now is I'm going to plug in the process at time point t minus 1 into this expression. And then I'm going to collect those. So then, of course, it's easy to see what this is going to be. So that zt is going to be, of course, zt minus 1, which is here. This is zt minus 2, plus the noise at time point t minus 1, and then plus the noise at time point t. This is basically what it would be, right? And then after all, when you basically looking at it just a moment, okay, I'm checking whether this is working. So then, of course, this is basically what considered to be the first iteration. So you basically substitute zt minus 1 with this expression. And you just saw what it was, but I'm going to just rewrite this in terms of a different order. So you have the process at time point t minus 2, and then the noises at time point t minus 1 comes first, and then time point t. Okay, so we're going to put time point t, the noise at time point t first. Okay, usually it would basically was in the previous representation it was second, but that's it. Okay, so then you'll have two noises, or some of those noises basically, right? And you would continue. So you can basically also address basically the observation at time point t minus 2 then, because that would be the previous observation, which is or was at time point t minus 3, with the noise at time point t minus 2. And then you could substitute actually the process at time point t minus 2 with this expression because that's already here. Okay, what will it be? So you can see actually what it will be. So the process at time point t would be, again, I'm going to replace that by this expression. So you see the process at time point t minus 3 plus the noise at time point t minus 2 plus those noises that you just saw. And I'm going to put them in different order. So actually, I mean, you would rearrange it after that, okay, because that's not order. So I'm going to start by t, then t minus 1, and then t minus 2. So I'm going to change, I'm going to basically permute those noises. So then you have the noise at time point t minus 1, and then at time point t minus 2. So that's basically how it's going to be, and that's going to be your second iteration. So I'm going to substitute basically the process at time point t minus 2 by this expression. You see it now. All right? So that's going to come here, and that's what it's going to yield. All right? So you saw it already. I'm not going to. So now you can clearly see how this evolves. All right? And now we're going to do this t minus 1 times. Okay? So here, these are the noises. And yeah, so basically if you do it t minus 1 times, I'm going to call it the t minus 1th iteration. I'm not sure if you can call it like that, but let's say I would. Okay? Then you have actually, I mean, this is basically how you come up with. You have the starting value of the process. So let's say this is actually the process at point 0, right? And if we assume that, so you go back in time. And then the last one would be actually at time point t. So your first so you have epsilon 1, epsilon 2, epsilon 3, and so on. And the final one is going to be t. So, and yeah, and that's it. So I'm going to write it basically this sum of those noises here. So that is the cumulative sum of those noises. You see? And that's going to be a random walk. That's going to be important next week. So I'm going to consider asymptotics based on the sum of these noises. Okay? So you integrate the noises. I'm not sure if you basically have seen that. Okay? So you integrate those noises because that's basically what it would be. So let's say, okay, whether you understand this or not. Okay? I'm not sure if you do, but let's see. So first off, okay, let's say, just for the record, so you see the representation. So you have the sampling point, time. Okay, so 0, 1, 2, 3, 4, and 5. And let's say, without loss of generality, the starting value of the random walk would be 0. Okay? Leave that column, please. And I want to basically, let's say you have a sample of noises first. Okay, so you have those noises first. Let's say at time point, at time point 0, there is none. Okay, so there is none. Okay, here let's say there is none. Okay, we are going to start with, let's say, I don't know, 2 or so, 5, negatives 2, 3, and 1. Okay, so these are the noises, let's say. And you would get basically the random walk. Okay, and that would be the cumulative sum of those noises. That's simple. Okay, so we're going to assume that without loss of generality, the starting value would be 0. Okay, and then comes the first noise, which is 2. So you accumulate the noise. Then 7. All right, you see? Then it goes back to 5. And then 8. And then 9. So that is the cumulative sum. And that's going to degenerate, basically, the random walk. You understand it now? Okay, so this is how it works. So we're going to, if you go from the noises, okay, so then of course, actually, I'm not sure if you're recognizing it, but if you look at the increments of the random walk, okay, these are actually equal to the noises. So the noises here are actually the increments of the random walk, right? So that is including basically the difference operator. That's what you see here, okay? You see? Does that make sense? Okay, again, I was assuming that the starting value would be equal to 0. It's not necessarily 0, but why not? Okay, so let's say you start there. You understand it now? So again, if you go this way, you're differentiating the process, right? And if you go this way, from the noises to the random walk, you're integrating it. So a random walk is actually, technically speaking, nothing but an integrated noise. You understand what I'm saying? So you accumulate those noises, right? Is that difficult to see? No, right? I don't. I mean, I hope it's not. So yeah, that's basically what it would be. You understand it now? Okay, so the concept again. You can differentiate a process or you can integrate the process, right? You can basically go both ways. You could also look at the increments of the increments, by the way, right? But the issue will be, and that's something which I want to mention here, the noises are stationary, right? And the random walk is not. Okay, but it has stationary increments. That's the point. That's going to be important. Okay, we're going to discuss it further. So not now, but we're going to basically discuss it further. So here we'll see that later on as well. Okay, now, if you put the drift to it, right, then you would need to add basically a constant all the time, but in a cursive way. If you do this, okay, and you have it over here, that this is going to be degenerating a linear trend to it. So not just the cumulative sum of those noises, but also with a linear trend. Okay, why? I mean, again, you can try it out so you can see basically how it will be. I mean, this is also true for basically for the starting point. Okay, so you can basically start from here. If you're not seeing this, let's say the starting value would be equal to 0, and the first value would be equal to the starting value plus the noise, and plus the trend, right? So that would be basically, that is also true. So you have the trend, the trend, plus the starting value, which is 0, plus the first noise. All right? So here you would basically, at point 1, that's basically how it evolves. At the second point, okay, second time point, that would be also true. So you have delta plus the previous observation, which was at point 1, plus the noise at time point 2. And now if you substitute, all right, so you can basically substitute Z1 by this expression, you're going to get actually the parameter delta twice. So you have delta plus delta, which is 2 times delta, right? Here it is. So if you basically at the second point, you're going to get delta times 2, right? That's basically delta times 2. Here it comes. So you have it twice, you see? And then you have the 2 noises, epsilon 1 and epsilon 2. All right? So I'm going to start from behind. Epsilon 2 plus epsilon 1. This is how it goes. All right? So that's basically how the iteration comes. And this is explaining why you have actually time reflected to it. So there is going to be a linear trend in the data in addition to the cumulative sum of those noises. That's going to add it up if you integrate the process. You understand what I'm saying? You integrate basically the noises in addition because these evolve around a constant. So there's always going to be a constant around. And that's going to be there twice after that. Okay, so that's basically how it will be. Okay, you're going to see this in the video, so don't mind basically if you're deleting it. But some people ask, okay, where does actually the trend comes from? Why it's not just a constant? And that explains it, because you would integrate it. So you have a constant plus the noise in the first place, and then you have constant twice for the second iteration. Okay, if you go start basically from the starting value. All right, now I was showing you the paths of zero and random walks, and then basically the process is called random, or simply random process, because anything can happen. So regarding noises, can be evolving like this, or like this, or like this, or like this. This is not actually, this is typical. I mean, you can see the difference between a random walk and a stationary process, by the way, right? It's unpredictable. That is a major characteristic. And I'm not sure whether it has a trend or not. So it might appear that it has a trend, but maybe it doesn't. So you would not be able to distinguish between that. But you could add a linear trend, it will still be a random walk. Okay, so sometimes it's not even visible that there is no drift in here, but you could assume that there is a trend here, right? but that was not. So the drift was 0. Okay? So it's not predictable, by the way, that process, if it's basically pure random walk. That's how it's called, pure random. All right? Okay. Now, you've seen that. So I'm going to discuss further properties, but actually next week we're going to dive a little deeper regarding the properties. I just basically showed that this time that the process is not going to be stationary, although their increments are. Okay, so the increments are stationary, because if we differentiate the random walk, it would be actually, the increments would be stationary. So I'm going to look at basically properties of the random walk. Now, again, the first property is that its increments correspond to the noises. So it's technically, I mean, you can see this over here. So this is actually the random walk by definition. And if you arrange this equation, okay, so that would be basically the current observation minus the previous observation would be actually equal to the noise, so that the increments of the random walk are going to be the noises, right? So the random walk is technically saying the cumulative sum of those noises. This is the difference separator that you saw, okay? The difference between basically the current observation at time point t. Let's say time point t is the current observation point of time, current point of time, and the previous one. So if these are daily observations, that would be basically the increment. And then increments are actually those noises, all right? So the increments are stationary, as you see, because the noise is stationary. That is stationary, so is the increments of the random walk. But the random walk is not. You understand the point? All right, so the random walk is not going to be stationary. I'm going to show you why. Because you have time dependency, at least for the mean or for the variance or for the autocovariance. Typically, the variance and the autocovariance are always going to be time dependent, as you will see. Because in the previous case, the mean, of the random walks that you saw were 0. Now, the mean is going to be actually equal to the expectation or the starting value plus the linear trend. If the drift is 0, then of course the mean is going to be equal to the expectation of the starting value. And if the starting value is 0, then it's simply just going to be 0, by the way. Okay? But however, the process is not going to be stationary. Okay? So you can see actually the time dependency of the mean if you have a drift. If not, then of course it's not, but it's not going to be an issue. Now I'm going to come back to the original representation. So you have the cumulative sum of the noise plus the linear trend plus the starting value. And I'm going to calculate the expectation of that. The expectation of a sum is going to be the sum of the expectations. So that's going to be the expectation of the starting value, whatever that is. And you have a linear transformation here because this is a constant. So even though it's a linear trend is a constant, it's no random, right? And then a constant plus a random variable because the sum of the noises is random. So then you have basically a linear transformation of that sum is going to be, the expectation of that is going to be the linear transformation of the expectation. So you take that out from the expectation operator and consider the expectation of the sum. Now I told you before, I think it was last week, 2 weeks ago, that the expectation of a sum is going to be the sum of the expectations. I didn't do it, but I want to stress this here. So the expectation of a sum, just put it simple terms. Okay, here it are. So this one is going to be equal to the sum of the expectations of those noises, right? You see? So you can bypass basically the expectation operator by the sum. Now, these expectations are going to be 0, all of them, right? So the sum of those zeros is going to be 0 after all. So the expectation of that is going to be 0. And this means that, of course, this is going to be basically dropped by from the expectation. So the mean is going to be time dependent in general. And it's not the case if it has a drift. So if the drift is 0, then it's not going to be time dependent, by the way. That was the case of the paths of the previous random walks that you saw. They have actually a constant mean. But the variance is not going to be constant in general. So the mean is not constant in general either, okay? If it has a drift, it's not going to be, it would not be stationary. So with random walk with a drift, it would not be stationary anymore at this point, because the expectation would depend on time. You see, there is the time dependency. Of course, if the drift is 0, then of course there is none, but that's not true actually in general. Anyway, but the variance is never going to be time independent. So no matter what you do regarding the variance of the random walk is always going to be proportionate with time. Okay, so you take the variance of that. I'm going to show you first what it would be. Now, whether you assume that the random walk starts at point 0 or not is not necessarily important. If it's a constant, then it's going to be, the variance of that is going to be 0, but it's going to be actually proportionate to time. So it's going to grow by time. The variance is going to grow by time. That's why it makes it unpredictable. And it's going to be linear by time. Okay? Now I'm going to show you why. So first off, you would need to calculate the variance of that thing. Because, again, this is a representation of the random walk. And then, of course, the variance of a sum is going to be the sum of the variances in this case, if the random variables that are involved are actually uncorrelated. The starting value does not correlate with any of those noises, because the noises are not autocorrelated, actually, by the way. So it depends on anything, and that can be actually assumed. So the variance of that is going to be, the variance of the sum is going to be the sum of the variances. Now, the variance does not depend on additive constants. Keep in mind, because the variance of a linear transformation is going to be the square of the multiplicative constant times the variance of the random variable from which the linear transformation was constructed from, but not from the additive constant. Because, again, the linear trend is also additive here, and then that's going to be a constant, so its variance is not going to depend on it. So you can take it simply out from the variance operator. So the variance of that with the linear trend is going to be simply just the variance of it. All right? That's it. And the variance of a sum is going to be the sum of the variances if the random variables that are involved are not correlated, which they're not. Okay? So again, why would basically the noise correlate with the starting value of the process? They don't. Now, in this case though, and that's going to be important, the variance of a sum is going to be the sum of the variances. That's important here. Okay, why? Because the noises are not autocorrelated. We saw, by definition. If there is no autocorrelation, then the covariance is going to be, there is autocorrelation, which is 0. The covariances are going to be 0. I told you before that the variance of a sum is usually the sum of the entries from the variance-covariance matrix. But since the covariances are 0, you have basically the sum of the entries is going to be just the sum on the main diagonal, and on the main diagonal you have the variances. So the variance of a sum is going to be the sum of the variances, and since those variances are going to be all of them respectively sigma squared, you have sigma squared plus sigma squared plus sigma squared t times, which yields t times sigma squared. That's it. You see? So that's basically what that would be. This means that, and that is true with or without a drift, it doesn't really matter. So whether you have a drift or you don't, it don't matter. Even if you don't have a drift, this dependency is not going to go away. You see? All right? So the time dependency, Okay? So the variance is always going to be time dependent no matter what, whether you have a drift or not. And that's basically what it makes it unpredictable. It's going to be linear, basically, by time, which it actually is going to be an issue. All right? So we're going to discuss further properties, but again, stationarity is going to be blown up right now. So you cannot achieve it anymore. You see? It's not going to be possible. You understand the point, guys? All right? That's it. Now, I'm going to look at the autocovariances also. Okay, so let's look at the autocovariance of the random walk. There is going to be an autocovariance. And that is also going to be time dependent. And you're going to see how this works. So I'm going to look at basically the autocovariance of the process at time point t versus at time point t plus h. And it's going to depend on both at the sampling point as well as the time lag. The formula is going to be the starting value, or the variance of the starting value, which again, it can be assumed to be a constant. So at least you can get rid of that relatively easily if you assume that the starting value is at least some constant. But again, in general, it's not. So then you have basically the minimum of t and t plus h times the variance of the noise. So sigma squared, keep in mind, okay, so it's not the variance of the random walk, it's the variance of the noise. So which one is smaller? Again, it depends on basically the sign of h. So I'm going to basically just address this so you see what this would mean. So the minimum of the two depends on age, right? Which is smaller? I mean, depends on age. If age is positive, so if age is positive, right, then it's going to be t, okay? So, or positive or 0. So if in this case, it's going to be t. But if it's negative, right, if age is negative, right, it's going to be t plus h then. So that's basically the other one, if age is negative, right? So which one is smaller? Again, it depends on age, how far you would go, okay? If you go backwards or basically looking at future values. Anyways, but that's how the structure would be. I'm going to show that quick. So, but that means that it's always going to be time dependent no matter what. So you always have t in there. You can get rid of it. So that's basically also blowing up stationarity, by the way. At least if it's not, I mean, it was already blown up by the variance, but the autocovariance is also going to be time dependent. I'm going to look at those cases though. So let's make it basically 0 or at least non-negative. You can also incorporate basically the case where it is 0. But why, if it's 0, then how would you call it the autocovariance? That would be the variance then, right? That's t times sigma squared after all. Anyway, so I'm going to look at basically the case where this is greater than 0, so t plus h would be greater than t, which means that t is smaller than t plus h. So if you look at the process at time point t, this is how it evolves. You have the starting value, and you have those noises until, or the cumulative sum of those noises up to time point t. And if you look at the same thing again, and you go beyond that because you have basically the process at time point t plus h, you also going to have the additional ones until time point t plus h. There is a plus sign missing here, but I hope you don't mind that much. Okay? Now, the noises are not correlated, but if they are equal, they are. Okay, so those are the ones that correlate with each other, and those are the ones that overlap with each other. Those don't, right? Because they go beyond t, right? You go beyond t because age is greater than 0. So you would go beyond that. And yeah, so that means that this is what the variance of that is going to be. So the covariance, sorry. In this case, it's going to be t times sigma squared, which would be the minimum of t and t plus h times sigma squared, right? And of course, you have the covariance with the random variable with itself, which is going to be the variance then. So you would need to just look at the values that do overlap with each other. And since they're equal, their covariance is going to be their variance, right? So if you look at the covariance of a random variable with itself, it's going to be equal to its variance. Okay, that should be clear. All right, good. Now, but they don't autocorrelate, right? But they do overlap with each other. Okay, so the variance of that sum is going to be t times sigma squared. I mean, the covariance of that, because, and those are, or could be dismissed. I need to put another sign on that one too. Okay, now if h is less than 0, then t plus h is going to be less than t. So then you would basically stop at that point already. Here it is. So you have t plus h, a sampling point before it happens before t, right? And this means that there is, again, if you look at the processes, I mean, after that, there is no observation anymore. So let me just basically come to make that point. The process at time point t plus h, after that, there is no observation. You see? So these are gone. They don't happen because t plus h happens before t. Okay? And now those are the ones that overlap with each other, and there is t plus h of them. So their covariance is going to be t plus h times sigma squared, which is actually sigma squared is the variance of the noise. Okay? So that's going to be the smaller one. This illustrates basically the fact that the autocovariance is going to basically have this structure. So which one is basically smaller? Again, this is depending on it. But in this case, it's going to be t plus h times sigma squared. But keep in mind, t plus h is less than t this time, okay, because h would be negative. All right, now let me collect those. Now the autocorrelation is going to converge to 1 as time increases, or time progresses, let's say. That's a property that I wanted to address as well. Why? Okay, let me recall, basically, the autocorrelation converges to 1 as time increases. That's a property that a random walk is, in addition, it has. So I was addressing the mean, I was addressing the variance, I was addressing the autocovariance, and now I'm going to also address the autocorrelation. And that is going to increase by time. It's going to converge to 1, okay, which is weird, right? Because that would mean that it will have actually a perfect linear relationship between two observations of it, at least in the long run, okay? That's interesting. Now, why is that? Again, let me recall that the variance of the random walk looked like this. The variance at time point t looked like this. And the autocovariance looked like this. And if you divide the autocovariance, which is here, this is the expression, by the square roots, the respective square roots of that one and that one, right? And then you would examine what happens with this expression if t is converging to 1. You'll find that this is going to be, as t increases, so t tends to infinity then. Okay, so you take the blue expression divided by the square roots of these. Okay, you'll find that the significance of h is going to decrease, right? So in this case, if h's would be equal to 1, they would be equal to each other. All right, so again, as time increases, the significance of the time lag disappears. And that's the reason why basically the autocorrelation converges to 1. I'm going to summarize it. Okay, so basically that was the variance, that was the autocovariance, and the mean is, or was here. Let me recall that. There was a linear trend. So again, stationarity can no longer happen. The process is not stationary because, again, the variance is time dependent. That should be fine. The autocovariance too, but, right? One condition is basically violated. It's basically linear in time. And I'm going to put basically that property which I found here as well. So the autocorrelation would converge to 1 as time increases, which is weird, right? Because this would indicate that there would be a perfect linear relationship between the two observations. But there is going to be a perfect linear relationship between the two observations in the long run, even if the time lag is not 0, right? Okay, well, the process cannot be stationary. That is sure the case. Without a drift, it doesn't really matter. So this is also true if it has no drift. If it has no drift, then the only thing that disappears is here. All right? But it's still not going to be stationary. It doesn't really matter. So it don't matter whether you would consider it for basically the drift or you don't. Okay? All right, guys, these were some basic properties, and I'm going to look at some asymptotics next week. And from those asymptotics, I'm going to develop the Wiener process. This is going to be our next topic, okay, that we're going to look at. Okay, these are easy ones. It's not going to be a difficult one, but that's basically what it was for today. Okay, let me take questions. Maybe you got questions to those things. If you're not, don't, I assume. Then, okay, then see you next week. That was it for today. Take care. That was it. Thanks. Okay.